Hi to everyone, welcome once more to a video in our YouTube channel. In today's video, we are going to be solving the problem that came in the mathematics paper 1 question of the entrance examination into the National Advanced School of Engineering Yaoundé in the year 2020. We are going to be solving. We have half into 1 plus 1 on n minus n plus 1 times 2n plus 1 all divided by 12n cubed is less than the ln of p of n, which is less than half into 1 plus 1 on n is allocated for 1.5 marks. And lastly, the c part is asking us to hence deduce the limit of p of n when n tends to positive infinity. It is allocated for 1 mark. Alright, so without wasting much of your time, we are going to go directly to the solutions of the various sub questions in problem C, in our problem that is part C. Alright, so here are the questions that have been displayed to us. So we begin straight away with the solution with so we have question 1 here. It's asking us to show that for all values of t greater than 0, we have t minus t squared on 2 less than the ln of 1 plus t, which is less than t. So I'm going to show you how to go about this question using a method. Now there are many methods actually, but I'm going to show you a very short method that you can always use to approach questions like this, and it always works, always. Okay, so the first thing is that we are going to divide the given inequality into 2 parts, because we have this inequality. We need to show this. So if I show that t minus t squared on 2 is less than the ln of 1 plus t, and later on I show that the ln of 1 plus t is less than t, then I can conclude that this inequality is true. So I show this first part of the inequality, and then later on I show this other part of the inequality. Okay, so showing the first part of the inequality is the same as showing that t minus t squared on 2 is less than the ln of 1 plus t. But now these two functions are always difficult to compare two functions. So it is preferable to subtract the ln of 1 plus t from both sides of the equation, and you compare this function with 0. It's better to compare a function with 0 than to compare a function with another function. Alright, so maybe if I let my f of t to be this function on the left, now all I have to show is that this f of t is less than 0. If I am able to show that f of t is less than 0, then I can conclude that t minus t squared on 2 minus the ln of 1 plus t is less than 0, because that is my f of t. Now remember, we are in the interval t greater than 0. Okay, so here's a trick. We begin. If I begin with the very first value of t, and I compute f of that value, and the result is less than 0, and I find out that my function f of t is monotonic decreasing, then as a consequence my function f of t will be always less than 0. Let me try to indicate on a graph. Now here is my graph of f of t against t. This blue graph here, I see my f of t0 is 0. Let's just say our t started from 0, and since it is f of t0 is 0 and my f of t is monotonic decreasing, then automatically it always lies below the t-axis, meaning it is always negative. If I also take this other curve here to represent f of t, and then I take t0 maybe not at 0, maybe somewhere here, I see that f of t0 is having a value which is less than 0, as we supposed here. So having a value less than 0 and monotonic decreasing, then automatically it is always negative, meaning it lies below the t-axis. The reverse goes for if it is monotonic increasing and the f of the original value of the very initial value of t is greater than 0. So if it was maybe our f of t0 was greater than 0 and my f of t is monotonic increasing, then definitely my f of t will be greater than 0 because it's going to be monotonic increasing and the very first value is greater than or equal to 0. So it's always going to lie above the t-axis. So that is a trick that we are going to use here. I read it again. F of t0 is the initial value of t. If f of t0 is less than or equal to 0 and the function f of t is monotonic decreasing, then the function f of t is always less than 0, and here is the illustration. So that is all we need to verify. We need to just verify these two conditions in red, and then we conclude that f of t is less than 0. Let's begin. Maybe since they say t is greater than 0, means we cannot take 0. So let's maybe take the first value of t to be 1. You can also take half 0.5. It all depends on you. You're still going to get the same response at the end. So if I take 1 as my initial value of t, f of 1 is I just come here, I fit anywhere I see t, I fit 1. So I have 1 minus 1 squared on 2, which is 1 minus half, then minus ln of 1 plus 1. Now 1 minus half is half minus ln 2. Now half is 0.5 and ln 2 is 0.69. So when I subtract the 2, it's going to give me a negative value. So I see that my f of 1 is less than 0. First condition satisfied. Now I need to verify if the function f of t is monotonic decreasing. So when is a function said to be monotonic decreasing? When its first derivative is always less than 0. That's then you can say the function is monotonic decreasing. So I need to look for the derivative. So I compute the derivative of my function. So I compute the derivative of each function present in my function f of t. So we begin with t. The derivative with respect to t gives us 1. Now t squared on 2, the derivative gives us t. Now the ln of 1 plus t, to differentiate, we differentiate the interior, which is just going to give you 1 with respect to t, and we divide by the interior itself. So we get 1 over 1 plus t. Now from there, you can maybe look for the LCM. You get this. You take like terms together, and then you have negative t squared over 1 plus t. Now our aim is to verify if this function is monotonic decreasing, meaning that we need to verify now if this new function here, that is f prime of t, is always less than 0 for all values of t that are greater than 0. So let's see how we can go about it. Now we're being told that t is greater than 0. It means that t squared will also be greater than 0, because t squared is just squaring t. The square of anything is greater than 0. Now since t is also greater than 0, it means that if I add 1 to it, it will be also greater than 0. That one is clear. It means that what if I take the ratio between two positive terms, they will also be positive, because greater than 0 means you're positive. So t squared greater than 0 and t plus 1 greater than 0 means the ratio between the two will also be greater than 0. Now to get this function here, I need to multiply both sides of this inequality by a negative sign. So multiplying by a negative sign, the inequality sign changes to less than. But this whole function here is what? My f prime of t. So I see that my f prime of t is less than 0. And since f prime of t is less than 0, then my function f of t is monotonic decreasing. And we can conclude that since the f of 1 is less than 0 and f of t is monotonic decreasing, then f of t is always less than 0. Since f of t is t minus t squared on 2 minus the ln of 1 plus t, then this function here will be always less than 0. And we are done with the first part of the inequality. Now we are going to use the same principle to solve the second part of the inequality. So 1.2, we are now showing that for all values of t that are greater than 0, the ln of 1 plus t is less than t. That is this part. Now we do the same thing. We cannot compare two functions. It's always bizarre to compare two functions like that. So it's preferable we compare a function with 0. So I subtract t on both sides, I get this. Now maybe I let my f of t now to be the ln of 1 plus t minus t. And our interval of t is that t is positive. So the same principle, if f of t0 is less than 0 or equal to 0 and f of t is monotonic decreasing, then my f of t is less than 0, meaning it is always negative. Now we are going to begin. Let's say f of 1 is equal to the linear of, I replace t with 1, the linear of 1 plus 1 minus 1, which is the linear of 2 minus 1, but the linear of 2 is 0.69 approximately, so it is less than 1. So subtracting 1 from it to give us a negative value. Now the second, we compute the derivative and we verify the concept of it being monotonic decreasing if it is true. So the derivative of f of t, when I differentiate the linear of 1 plus t, I get 1 over 1 plus t. When I differentiate t, I get 1. Now I can look for the LCM and I simplify, I get this. Now this new function here is my f prime of t. I need now to verify if this function is less than 0, then I will conclude that f of t is monotonic decreasing. Now we had t greater than 0, it means t plus 1 will also be greater than 0, because I am adding a positive number to a positive number, it's also going to be positive. Now when I take the ratio between two positive numbers, t greater than 0 and 1 plus t greater than 0, I'm also going to get a positive number. Now to get this function here, I multiply both sides of the inequality sign by negative. So multiplying the inequality sign changes. So this function on the left hand side is f prime of t, which is less than 0. Hence we can conclude that our f of t here is monotonic decreasing. And since our f of t is monotonic decreasing, then it is always less than 0. Since it is monotonic decreasing and for the a guessed initial value of t is less than 0, then we can conclude that the function f of t is always less than 0. So with that, since we have proven the first part, which is this part, and we have also proven this other part, then we can conclude that this inequality is true for all values of t that are greater than 0. Alright, so let's move on to question number 2. Question number 2 has an information. Given that n belongs to the set of natural numbers, here is supposed to be n star, meaning 0 is excluded. We have a certain product, a product from 1 plus 1 on n squared right up to 1 plus n on n squared. Now the very first question is asking us to prove that the sum from k equal to 1 to n of k squared is equal to this quantity. So it is not so obvious, so we are going to use proof by mathematical induction. Alright, so we begin with letting the statement p of n be the given statement, and then we are trying to prove that this statement is true. So to prove by mathematical induction, we follow 3 different steps. First, we begin with a base case to test if it is true for the very first value of n. So for the very first value of n, that is n equal to 1, my statement p1 is saying that the sum from k equal to 1 right up to 1, because I'm replacing n with 1, of k squared should be equal to, anywhere I see n here, I replace it with 1. I simplify. This is summing from k equal to 1 to 1. It means you are not summing anything, you're just summing, you're left just with 1 squared. So 1 squared is 1. Now on this right hand side, if you simplify, this is going to give you 2 times 3, which will give you 6, times 1, which will give you 6, divided by 6 will give you 1. So p1 is true because the left hand side is equal to the right hand side. So the statement p1 is true. Now after verifying if the statement is true for the very first value of n, we now introduce an induction hypothesis where we suppose that the statement is true for n equal to a certain let's say variable arrow. Now maybe you might be confused why we're not taking k. We are not taking k because in our original question we have k there, so we cannot say suppose true for n equal to k. Is going to you end up doing nothing at the end. So you suppose true for n equal to arrow. Alright, doing that, it means that the statement p of arrow is true, meaning anywhere I see n, I put arrow. So the sum from k equal to 1 to n becomes the sum from k equal to 1 to arrow. Now you see I have indicated the arrow in a different column, as you can see. Now after introducing this induction hypothesis, we are now going to use this induction hypothesis that we supposed that the statement was true for n equal to arrow, and then we prove that it is true for n equal to arrow plus 1, and then we conclude. So our induction step, is proving that the statement is true for n equal to r plus 1. Now, proving that it is true for n equal to r plus 1, it means we need to prove this identity, that is the sum from k equal to 1 to r plus 1 of k squared should be equal to this. Just replace, anywhere you see n here, you replace with r plus 1, you're going to get this right hand side. So let's begin with the left hand side, and then we see how to get the right hand side from the left hand side using our induction hypothesis that we assumed. Alright, so the left hand side says the sum from k equal to 1 to r plus 1 of k squared. Now let's write it down what it is actually. So summing from k equal to 1 to r plus 1 is 1 squared plus 2 squared. When k is equal to 1, we have 1 squared since it is a sum, plus when k is equal to 2, we have 2 squared. Right up to, before I reach the r plus 1 term, I will first of all pass through the r term. So k equal to 1 to r plus 1 is the same as k equal to 1 to r and then the r plus 1 term. So the sum that has been indicated in red can simply be written as the sum from k equal to 1 to r, because I'm summing from, that's 1 squared plus 2 squared plus right up to r squared is a sum from k equal to 1 right up to r, then plus my r plus 1 term. Now my induction hypothesis told me that this is true. So if it is true, it means that I can replace the value here, and then the final equation here, or the final result here, is also going to be true because this is true. So replacing it, I get the left hand side, which is this, to be equal to this sum now becomes what I assume true, that is this, then plus r plus 1. Now I can factor out r plus 1. I'm going to get this. Now let's try to simplify the interior to see what we are going to get. Alright, so the interior part, we can look for the LCM, and then we try to add like terms together, and then we factor it out. That's the factors of 12, that if you add, you get 7, and you multiply, you get 12, 4 and 3, and then you now try to factor out this equation using the factorization method. You're going to get this. So from there, we now come and replace it with its equivalence, and we get the r plus 1 that is outside here times r plus 2 times 2r plus 3, all divided by 6. So we can conclude that what? That our statement p of k plus 1, sorry, p of r plus 1, not k plus 1. So the statement p of r plus 1 is true because this is what we are supposed to prove, as you can see, and here we have it. So from there, we can now draw our conclusion. Since it is true for n equal to 1, as we saw, and it is true for n equal to r plus 1, not k, sorry, and it is true for n equal to r plus 1, as supposed true for n equal to r, then it is true for all values of n in the set of natural numbers. So that's it for proving it, that the sum of squares is equal to this identity. Alright, the b part of the equation, we are supposed to prove this. So I'm just going to go through it gradually, but very fast and very brief. So we have been given our product p, which is the product from 1 plus 1 on n squared right up to 1 plus n on n squared. Now we have to prove that the limit of this product lies between this, that is half into 1 plus 1 on n, and all of this. Okay, so if p of n is equal to this, so to prove this, I begin by looking for the limit of p of n, because if I don't have the limit of p of n, I cannot prove this. So I begin by looking for the limit of p of n. So the limit of p of n is the same as taking the limit of everything here. But now we know properties of logarithm. The limit of products is the same as the sum of the limits of each term in the product. So the limit of this times this times this times this becomes the limit of this plus the limit of this plus the limit of this plus right up to the limit of this. Now we can write this as a sum, actually, because we are summing the limits. So we can write it as a sum as well. The sum from k equal to 1 to n of the limit of 1 plus k on n squared. As you can see, the n squareds remain the same, but what is changing is 1, 2, 3. So the numbers are increasing by 1. So simply I'm going to call it, I'm going to call the number k, because I'm summing from k equal to 1 and k is a natural number. So if you like, you can replace here. When k is equal to 1, you have the limit of the first part, plus when k is 2, you have the limit of the second part, right up to when k is n, you have the limit of the n part. Alright, we proved in the very first question this identity, this inequality, sorry. So we are going to use it here. Now how is it going to help us? Just watch and see. Now if I compare the ln of 1 plus k on n squared with the ln of 1 plus t, it is almost the same because I have 1 plus and 1 plus, you see. So with that, since I have a ln there, then it already is my work here because I have a ln here. And then this ln here, I'm supposed to prove that it is bounded by some two sequences. That's what I need to prove. And here I see that this ln here is bounded by two things also. So from there I get a clue on how to proceed. So if I set t here to be k on n squared, to have this ln here, then doing that, automatically I can replace t with k on n squared in this inequality because I proved already that it was true. So replacing t with k on n squared here, I get k on n squared minus t squared becomes k on n squared all squared divided by 2. I also replace. Now from there I can take the sum on all sides, that is the sum on this side, the sum at the center, and the sum at the upper bound. So taking the sum, we take the sum of this, we take the sum of this, and then we take the sum of this. But what do you discover? The sum of this is just our ln of p of n. So we are getting closer to the answer because this sum at the center here is just the ln of p of n, as you can see. Alright, so from there, we properties of sums. The sum of this difference is the same as the difference of the sums. So we have the sum from k equal to 1 to n of k on n squared minus half times the sum. Now when I square this, I get k squared on n raised to the power 4 because it's k on n all squared. Now the middle term becomes the ln of p of n, and now the upper bound becomes the sum from k equal to 1 to n of k on n squared. Alright, so from there now, since my sum depends on k, it does not depend on n now becomes, any function in terms of n is a constant because I am summing from k equal to 1. So it depends solely on k. So from here I can factor out 1 on n squared. From here I factor out 1 on n raised to the power 4. This middle term is ln of p of n. From here I factor out 1 on n squared. So factoring out 1 on n squared from the first sum, I get this. From the second sum here, I get this. My middle term remains intact, and then from the upper sum, I get this. Now, we know we proved already the sum from k equal to 1 to n of k squared. It is this. So in this place here, I'm just going to replace it with its identity as we proved. But now, what is this? We can identify this as an AP because summing this is the same as 1 plus 2 plus 3 plus 4 right up to n. And the first term is 1 and the common difference is 1. So we can find the sum of this using the sum the sum of the first n terms of an arithmetic progression. So it's simply n over 2 into n plus 1. N over 2 into n plus 1, or n into n plus 1, all divided by 2. Using the formula, that's the formula n over 2 into 2a plus n minus 1 times d, where a is the first term and d is the common difference. You do it, you're going to get this sum as this. Alright, so from there we just fit, here becomes 1 on n squared. Now this sum is, you fit with this identity here. So you get this minus 1 over 2n to the power 4 multiplied by the sum of squares less than the ln of p of n, which is less than all of this quantity. Now let's try to simplify this quantity here and this quantity, because you can see that this quantity here is the same as this quantity here, so we'll just simplify one of them. So simplifying, we see the n's first of all cancel, 1n cancel, and then we have half. Numerator becomes n plus 1, the denominator becomes n. We can take n plus 1, we can take each term in the numerator and divide by the denominator, since they both have a common denominator. So you have n divided by n, which is 1, plus 1 divided by n. You're here. So you have gotten this first part. Now what about this part? We need to simplify this. Now we can see clearly n here goes with n to the power 4 here to give us n cubed. Now 2 times 6 gives us 12, and that is it. And the numerator becomes n plus 1 times 2n plus 1. That's it, we are good to go. Now the last part here is the same as this guy here, because it is 1 over n squared times the sum of an arithmetic progression. So with that, we are done with the second proof of B. Endeavor to subscribe. If you have not understood anything along the way, try to post your questions or your worries in the comment section so that we can know how to explain better. Alright, the very last part is asking us to deduce. It is a hence question, so hence deduce the limit of P of n when n is tending to positive infinity. So this is also something that we need to pay keen attention to. So just follow up the procedure. So this is going to help us because we have P of n, we have the line of P of n here. So having the line of P of n here is going to help us get P of n. If we take exponentials on both sides, though, we are going to get P of n, but since we need a limit, just follow what I'm going to do. So firstly, I'm going to find the limit of the upper bound of the line of P of n. The limit is giving me half as n tends to infinity, positive infinity. Because as n tends to positive infinity, 1 over n tends to 0, 1 plus 0 tends to 1, and then half times 1 tends to half, so we have half. Now second, we find the limit of the lower bound. This limit here gives us half, and this limit here gives us 0, because the polynomial in the denominator has the highest degree. In the numerator, the polynomial has a degree of 2. In the denominator, the polynomial has a degree of 3. So as n tends to infinity, this limit gives us 0. So we are just left with half minus 0. So it tends to half. So we see that what the limit of the upper bound and the limit of the lower bound of the line of P of n are the same. It therefore means that by the sandwich theorem, the limit of P of n is equal to that limit. Now we are asked to find the limit of P of n. We have gotten the limit of the line of P of n. Now let's get some basic properties. First, with limits, the limit of a line is the same as the line of the limit, provided that limit exists. So the limit of a line is the same as the line of a limit. So with that, we use that property, and here the limit of this line becomes the line of the limit. Now next property, the line of a limit is if the line of a limit is equal to a constant a, then the limit is equal to e raised to the power a, meaning the laws of the exponential law also holds, because line is the same as logarithm to the base e. So logarithm to the base e of something equal to a. To remove the logarithm, we take exponentials on both sides, and we get the line of that quantity is equal to e raised to the power the constant. So from there, we are going to apply it here, and since we are finding the limit of P of n, means we are just finding this. So exponential here, you just get this limit, and exponential here, you get exponential to the power half, which is the same as the square root of e. So finally, we are done with this problem. Now